The best of mornings to my M4 squad. We're finishing the homework today. So anybody who got a perfect score in the midterm will actually pass the class today, which is a wonderful thing. So we're working on three different topics today. The first one is a continuation to what we were doing last week that has to do with binary trees, where we're talking about full binary trees and what's the shortest one we can make for a certain amount of nodes. That's what we're going to do first. We're going to do it first on the whiteboard to understand the structure, and then we're going to be working with a code. Earlier today, I linked you guys all the 5 codes, but I'm going to be relinking them as we get to use them. So the very first thing we're going to do is I am going to draw the binary tree corresponding to the data in my question tree. Look at what I'm doing, and when you think you've understood how this works, grab your notebook and a pen or a pencil and draw your own. Then when you've drawn your own, post a picture on the channel, please, so I can make sure that everybody has understood correctly how they are supposed to draw their trees. So the important thing here is the sequence of numbers. Mine's 96, 39, 72, 73, 74, 77, 19, 86, 41, and 6. So that's the data you need to have at hand to be able to do what I am going to do. Okay, so let's head to the whiteboard straight up. Okay, so this is very related to what we already spoke about last week. So this should be kind of easy if you were on board last week. So the nodes are going to be arriving one by one. Imagine them like dropping from the top. And the very first one is going to create the root of the tree because it's going to be the very first node we have. So I'm going to write the whole sequence here first. I'm going to have a 96, a 39. Then I have 72, 73, 74, 72, 73, 74. Then I have a 77. Then I have a 19 and an 86. 19 and an 86, followed by a 41 and a 6. So I take the first one, it falls, it goes into the root. It's done now. And now remember, the rule here is that smaller values go to the left, larger values go to the right. Everybody enters through the roots. Like imagine these are the doors. Like these are the doors to come into the tree. Everybody has to go through here. You cannot enter from anywhere else. There is no way that you would just kind of like skip someplace. You always have to enter through the root. So the second guy, 39, enters through the root. It's smaller, so it goes to the left. Then the next number enters. I'm actually going to put it a little bit higher because we're going to run out of space. So the 39 is going to be here. 72 enters. It enters through the root. It's smaller. It gets sent here. Now this is going to be recursive. It's larger, so it has to go to the right. Okay, so it's done now. 73 enters through the doors. It's smaller, larger, larger. Goes here. I keep making my lines too long. Okay, 74 enters through here. It's smaller, larger, larger, larger. 77 enters here. Smaller, larger, 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 and larger again. 19 enters here. It's smaller, smaller, goes here. 86 enters here. Smaller, larger, 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 goes down here. 41, smaller, larger, smaller. 6, smaller, smaller, smaller. So now why is this a binary tree? Because there's a maximum of 2 branches, and those 2 branches correspond to smaller and larger. If we wanted the tree to be able to deal with duplicates, like the same value being there many times, we would have to choose which direction the equals go. But we don't have to worry about that in this class. We're not going to have duplicates at all. So anything that's smaller, left branch, anything that's larger, right branch. So we should be okay. And now there's some terminology we don't need for the homework, but we need it for the exam. So it's best to practice. All these ones that don't have any other node hanging from them, they are going to be leaves. Each of them are leaves. The very first one is the root. The node that's above another is the parent. So 74 is the parent or the father or the mother, depending on the author's terminology in each textbook, of this one here. So this one is the child node. And if you have two children, you can have a left child and a right child. So now if somebody asks me, what's the parent of 73? It'd be 72. What's the left child of 73? It doesn't exist. What's the right child of 73? It's 74. So I'm going to send you guys a picture of my tree, and you guys are going to send me pictures of your trees. Please vote green when you're done with your tree, and vote yellow if you need more time to draw your tree. That way we know when to continue. I will be waiting. And I'll keep the phone on me so I can admire your pictures and let you know if there's anything funky about your tree. Just one by one, all enter through the root. You can never ever jump to a branch. You always recursively go from the root. If you start jumping because you think you know where it goes, you're going to mess it up in the exam. Takes a fraction of a second to go from the root downwards. Can you at least vote yellow if you're already working on your drawing so I don't sit here all day in case nobody's drawing anything? Okay, one person is done. It's always good to have at least one student who's doing something. 3 people are working on theirs. I'm really interested to see the one that's already done. And this is definitely happening in the final exam. You're definitely doing this. You're getting a sequence of numbers and you're putting those numbers in a binary tree. Then you're going to be answering questions like, which one's the root? How many leaves are there? What's the parent of this node? What's the child of this node? So it's important to practice this pretty well, straight up, because it's a lot of points in the exam you get just by analyzing your binary tree. Four people are done. Nobody's showing me their tree. Let me get on the computer so we can look at the trees and analyze them together when they start showing up. Okay, there is one. Okay, 74 smaller than 86, which is smaller than 90. This branch is fine. Everybody here is smaller than 74. 6 is smaller than 13. Everybody here is larger than 13. This one's larger than 55. This one's larger than 18. Okay, this is a perfect little tree. Anybody else? $37, it's larger than these, it's smaller than these. Okay, this one's perfect too. Remember to vote green when you're done, so I don't wait for you anymore. Another one. Starts with a 96 like mine, so everything's gonna be smaller here. I'm a little worried about your 50. How did a 50 get here? Because this branch is only for the stuff that's smaller than 34. So this 50 is not where it belongs. Remember, you always have to go from the top. Is it smaller than 96? Yes. Is it larger than 34? It should have gone on the other branch. It can't be here. This 50 is in the wrong place. Let's look at this one. 98, 100. Okay, this is nice. There's a thing much like mine over here. All of this stuff smaller than 98, so we're fine. This is the only thing smaller than 37. Okay, this one looks good too. And now remember, the order in which the nodes arrive, that affects the structure. If the 79 would have been first, we would have a totally different structure here. So the height and the shape of the tree will depend on in which order did the numbers show up. You don't necessarily get the same tree if they show up in different orders, although you can get identical trees from slightly different orders because not every single arrival determines the creation of a new specific branch, which then would affect the later arrivals. We're still waiting for 5 people to finish and for a bunch of people to show their trees. If you're absolutely confident that your tree is correct and you're kind of ashamed of it, then you don't really have to show it, but it would be nice if we could look at them. Also waiting for the fix on Luis's tree with the 50 less stray. 3 people still working on their trees. Oh, there were more hidden numbers. 13, 14, 24, 70, 41. Okay, this one looks fine. Still 3 people working on theirs. And again, the only reason to draw this by hand is to learn what's going on. When you already know what's going on, you would never do this by hand because this is to make like essentially a database. So you would do this by computer. And that's what we're going to do next when everybody has their drawing correct. So we're going to figure out what this code, the subroutine ubicar, is going to do. And then we're going to work out from the drawing what the answer is going to be. And then we're going to do it also with code to make sure that our reasoning is correct and that we're not confused in any way. Still waiting on 3 people to finish their trees. In the meantime, I'll give you guys the link to the routine we're going to need to analyze. So you can start reading the code. We're not going to run this yet because we haven't looked at the other file it depends on. We're just going to read it for now so that we can do this by hand. Still waiting for these three people though. If you voted yellow and it's just totally not working out because your neighbors are being loud or your brother is screaming, well, you can just vote gray and do it later. Okay, this one, let's check. Everybody here is larger than 65, so that's good. Everybody here is smaller than 65, that's good too. This guy's smaller than this one, then it's a bigger one. Okay, the three is, you've jump shipped here. Three can't be here because three would be smaller, smaller, smaller. This three is lost. On the other branch is fine. The three is a stray. Okay, this is the 50 now better located. Okay, so from 96 we get a 34, then there's a 10 and a 6, this is okay. And a 22 and the 23, those are fine too. 79 is okay, 50 is okay, 54 and 58. Now it's perfect. One person still working on theirs. We need to fix Jose's tree. The tree simply needs to hang from the 26. In here, this is a little bit difficult to read because these guys are kind of like almost on the same level, so it's not super clear who's the parent of whom. I'm gonna suppose that the 42 is the root, but please put the children lower, don't put them next. No one's ever next to anybody if they're connected by a line. So from the 42, 75 is larger. Oh no, the 75, I don't know what's going on here. This is so weird because the 75 has like three different links, but this, I think this is a 57 or a 37. I can't read the letter. So these two are the same level, so I can't really figure out who's the root. And I don't know if this is a 5 or a 3. I'm sorry, I can't figure this one out. Here we have a 65, then 68, 70, 93, looks okay. All these are smaller, 34, okay, this is good, this is good. Okay, this looks perfect. Paulina's working on hers, and Jose fixed his. Waiting for one more yellow. Like it's okay to have two nodes on one same level if they're not connected by a line. Then being on the same level, it just means that they're siblings or cousins or something that they kind of like, they're similar depth or height, well, depth really, on different branches. But if they have a line connecting them, they should be clearly one above the other. So it's obvious which one's the parent and which one's the child. Otherwise, you can't really read the tree. Usually the little mistakes that some people have made where stuff ends up in the wrong branch, it's because they don't go all the way from the root downward. They think they remember where it goes, and then they end up putting it in a branch where it doesn't go. Never ever skip. Always make it drip down from the root to find the correct branch. If you think, oh, it's going to go here because it's similar than this number. No, 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 no. It might not work that way. It might be very similar to one number, but still go in a different place because there might be a number right between them that's in an intermediate node and sends things to different branches. Waiting for that one. Try reading through the lines 9 to 16 here if you already finished yours, because those are the ones we're going to be discussing in a sec here. That part is what we need to understand. And you can also already go in the row mode and put it in your idle. View raw. Remember, we're going to put it in a file. I made my idle dark mode because white windows get on my nerves. So I'm just gonna put the code here, but you can't run it yet. You cannot run it yet because it depends on another file we haven't looked at. So don't try to run it, just park it in your idle. Okay, looking at this one from Luis. A 29, smaller are the 16, smaller 3, 25 is in the right place too. Then it's from there, there's a 74, smaller is a 51, largers. Yeah, you kind of run out of paper, but I get you. It's exactly like mine. And when you make the lines kind of long, you run out of paper, but it looks correct. Es como la pared de cualquier vulca donde intentan escribir algo y se les acaba el espacio y pues luego ya no les cabe lo que iban a poner. ¿Qué te pongo? Abrazo. Okay, Paulina's is more readable now. I have a 42, smaller are the 11, and then the 6, larger than 11, but smaller than 42. There's a 19 and a 23. Lovely. Largers are a 75, smaller than that, there's a 57. Largers are 79, 81, 82. This is lovely. And one person still in yellow. Waiting for one person. Okay, I think we're good now. Okay, now it was somebody else? Man. Well, I hope they won't be horribly offended. I'll check the tree as soon as it's posted, but I don't want to make everybody wait for a long time because then they get distracted and then they don't really listen to me anymore. So we're not looking at this routine, ubicar, because we need to figure out for the homework, how many times will that be called if I'm looking for a 29 in my tree? And you're going to have a different number here too. So let's look at those lines of code and figure out what it's going to do. It's going to be a recursive routine like the binary search last time. So to find a value in a node, we're going to check if the content of the node matches the searched for one. If it does, we return true. So we don't make any new calls. If it doesn't match, and we're looking for something smaller, and there is a left branch, then we make a recursive call on the left branch. If we're looking for something larger, and there is a right branch, then we make a recursive call to the right branch. If the branch where we need to go doesn't exist, we return false. So let's go do this with the 29 on whiteboard. You look at what I do, and then you do it on your drawing with your number. Okay, I'm going to take some of these extra annotations away so that they don't confuse us. Just a clean tree. And I'm going to enter my tree through the root looking for 29. So my first call is here. Are you 29? 96 will say, I am not 29. 29 is smaller and I have a left branch. So it's going to make a second call here. Then we're going to be at the 39 asking, are you 29? 39 is going to say, no, I'm not 29, I'm larger, so it's going to send us to the 19. With the 19, we're going to ask it, are you 29? The 19 is going to say, no, I'm not 29, and I also don't have the child you're going to. So the 29 here is going to cause a false. This one's going to return a false. The 19 is telling the 39, no, it's not here. The 39 tells the 96, no, it's not here. So the 96 tells the user who made the original call that the 29 is not here. So I ended up making a total of 3 calls to the routine. I'm taking a picture and then we'll check this again on the computer. So imagine it like a building with like rooms and hallways and doors between them that you always have to enter through the lobby. Every single room has a guard. You ask the guard, where do you need to go? And he sends you to the correct place. And if the correct place doesn't exist, he sends you out. And what we're trying to figure out is how many rooms do we have to visit? So for me, it's going to be 3. And we can use the code to figure out which 3 they are. And also when we have the code, it means that we can fix it so that we don't have to do any manual drawing and we can just count with the code. So the first thing we need to remember is these things are only going to give us the true and the false. If we want to know how many times we go there, we could print, for example, the content of the node we are at. Now at this content. So we could count how many times are we going to print, and we would know what we're looking for. So I'm going to be wanting to look for a 29. So I'm going to modify this. You put here your number that you're looking for. And obviously, there's a tree here. We were putting some random numbers here to it. We're not going to put these random numbers. We're going to want to put my numbers there. So we could put 4 n in, and then what are my n's? I have a 96. I have a 39. I have a 72, 73, 74, 77. I think I clicked tabulator. I also have a 19 and an 86 and a 41 and a 6. So for each one of those, I want to add that value into the tree. So I create a tree and then I push the data that I want into the tree one by one. So this is an important change that I'm making here. I'm making the creation match my data. And then on the very bottom, I made the modification to get my own search instead of the search that it had as an example by omission. My Discord is acting so weird. So this is now the modified version that I have made. And I still can't run it because it still says that it's going to import from a file called árbol, a structure called árbol. The fact that it's in Spanish should kind of hint at you that this is a different file we need, that this is not going to be a file you already have. It's another file in my repository. I'm giving you guys the direct link to it. So we need to go get this other file. This other file explains what are nodes. Nodes have content. They have a left child and a right child. If the content is none, we print them as empty strings, etc. Then we have a method for adding new content. If it's smaller, it gets sent to the left. If it's larger, it gets sent to the right. And then there's like a class tree that is actually the node that's the root. And when you add to the tree, you're adding to the root. So I made this. You don't have to touch it, but you do have to have it. So I'm going to go to view raw. I'm going to take this. This is what people call object-oriented programming because I made classes and then I can make objects of those classes. So I take all that and I'm going to put it into a different file. And it's very important that this file, it needs to be called exactly what it says here. So it has to be called árbol with only lowercase letters. If you call it anything else, there's going to be a problem. So I'm going to save this file. I'm going to call it árbol. And it's going to be a Python document. I already had one, so it's been replaced. So it's very, very important that after you've saved it, it should say here on the top bar that it's called exactly that. No uppercases, no spaces, nothing weird. Just árbol.py. Nothing else. If you start getting errors, I'm going to want to see what does it say on the top of your window, and then I will scold you if it doesn't say árbol.py. Okay? So that's where that code goes. Now, when I run this code, it's first going to read that other file, árbol, to learn the structure. Then it's going to create a blank tree that doesn't have anything in it. Then it's going to fill it with data to become your tree. Then we have the routine, where we added the printout because we want to know how many calls it makes. And then at the very end, we don't actually have to even print whether it's a true or a false. We already know it's going to be a false in my case, and it doesn't matter for the homework whether it's a true or a false. We just want to know how many calls there were. So I'm going to search at the root of the tree for the value 29. To run this, I click F5. It's not saved. So I'm going to save it with some other name. Don't save it on top of árbol. That would be a stupid idea. Save it with some other name. It doesn't have to be other name as long as it's a different one. Taking a screenshot of that too, so you guys can't get confused. So we have two different files, and the one that we're F5ing, the one that we are running, is the second file here. And when you run this file, then you are going to get in your shell, the idle shell, the printouts. You count how many printouts there are, and that gives you the answer to the first question. I'm resetting the votes. And when you guys are done with this question, please do two things. First, vote green when you have gotten the right answer. If you got the wrong answer and there's some kind of an error, please vote red and post the error on Discord. If you need more time, vote yellow so we know to give you more time. Also, please send to the bot a direct message, writing in your own words, I don't care if it's English or Spanish, everything you've understood from this question. All the concepts related to binary trees, searching for values, and doing this on Python that you remember to be relevant to what we just did, so I can see what you guys kind of like picked up from what we were just doing. Then when everybody is green, we can start worrying about question number 4. Gonna go wipe the whiteboard in the meantime. And to entertain the ones who are already ready, I am going to link a GIF. I can remember what it's called. This one. Okay, so this GIF has to do with what we're going to do in question number 4. And you're going to pretty quickly understand why we're not going to do it by hand, because it's going to be a very uncomfortable table to fold because there's lots of little numbers. And it's easy to make a mistake that then propagates around, along the whole thing. Remember, if you send multiple messages to the bot, the new ones replace the old ones. When you vote, please don't leave an empty space between the exclamation and the vote, otherwise the bot doesn't know what you want to do. I want to send some stuff to the bot too. Kind of looks like we might have the situation under control. Nobody needs more time. Nobody's posting any error messages. Okay, looks like we have everything under control. So let's look at this next code then. For the question 4 that's explained in this GIF, what we're going to do is we're going to calculate how many operations do I need to make to convert one text into another. So let's say that somebody hung some letters in the door of an office, and now we need to change those letters because the person who used to work there doesn't work there anymore. Somebody else works there. And we want to make as little work as possible. So we need to figure out which letters to remove, which letters to substitute, which letters do we need to add to modify the text to the text that we wanted. This is this problem. It's the edit distance problem, also called Levenstein distance. And this is how like autocorrect works, trying to figure out that which of the words in a dictionary is the closest word to the one that you were trying to type, or also genetic testing to try to figure out like which genetic sequence is similar to another genetic sequence. You can do very similar things to this to try to figure out how far is one text from another text. So we're going to be working with this code here. I'm going to get the raw version of it, and we're not going to mess with the implementation of the method. We're just practicing calling it, and we're practicing making tiny little adjustments. So I'm going to make a new file in idle. We're putting the stuff here. I'm loving the tag cloud. Looks good. Looks like we're understanding what's going on. So with this edit distance code we have here, if the costs of the operations of addition are 1 to insert, 1 to eliminate, and 1 to replace, what's the edit distance between sábado and domingo? So the words we want to use go down here. And where do the costs go? The costs go up here. So CE is the cost of removal. CI is the cost of insertion. And CR is the cost of replacement. So you don't have to change them here. You could simply change them, providing them here. So I could put different values in here if I want to. If I save this, just going to call it ED. And I run it, it's going to give me the 6, which is my result. If I wanted different costs, let's say elimination would cost 3, insertion would cost 2, and replacement would cost 1, I would just put them in that order. Elimination, insertion, replacement. I would click F5 again, and I would get a different cost because I just changed the prices of the operations. Okay? So I'm going to put it back to how my values were, that were 1, 1, and 1. There is no touching on the inside of the method. You don't need to do anything at all there. We are just changing the stuff over here. The words and the costs. We're not changing anything else. Let me put this on Discord. So remember, the beginning, I didn't do anything. So the only thing you're changing is the call. When you run it, it's going to give you a number, and that's the number you're going to be putting in the box. So I'm going to reset the votes, so you can vote green again when you are done with this question. And if you're interested in how does this work with stuff like autocorrect or determining paternity in a genetic testing or determining similarity between viruses and whatnot, it makes a very lovely topic for your final project. So we could discuss next week maybe, or after you've completed your 50 points today, if you are interested to do your final project on something related to similarities of strings. I am also going to reset the tag cloud. So if you have ideas on what you could do if you had a method like this that tells you how similar one text is to another, you can also send the bot a text description of what your idea is, what you could do with this, so I can see if there's interest to work with this topic in particular. One person's okay. So here the most important thing is when you're reading your homework, it gives the costs in order: insertion, elimination, replacement. In the code, you're putting them in order: elimination, insertion, replacement. So it's really a reading comprehension exercise. In which order do you have to put the numbers? Respect the order in the code. So you're going to put the first number in the second place. You're going to put the second number in the first place. And you're going to put the third number in the third place. Also remember, I have two closing parentheses here. The first one closes the call to edit this, and the second one closes the call to print. If you skip one of them, you're going to get an error. I'm also going to link you guys the two codes we can use for the final question. You don't need both. You can use either one. They're both going to give you the same exact response. And the modifications we're going to make are going to be extremely similar. And I'm going to link a GIF for each. So let me link them in the same order. The GIFs, the first code goes with this GIF, and the second code goes with this GIF. Okay, 8 people are okay. If you need more time with the edit distance, please vote yellow so I know to wait for you. Okay, so nobody's acting like they need more time, meaning that we could go back to the whiteboard because I want to explain this on the whiteboard using a totally artificial example. But before we do that, let's take a quick look at the GIFs. So what's going on here with Kruskal's algorithm? We have a graph and we have these costs. We're going to pick the cheapest edge and activate it. So this costs 1, we activate it. This one's the second cheapest, 2, we activate it. Another that costs 2, we activate it. No more of cost 2, we activate a 3, we activate a 3. When 2 activated pieces connect, they become 1. Then I need to activate another 3 over here, another 3. Now all of this connected, and I still have one guy who's not connected. So I need to pick the cheapest potential edge to connect that. I need to get rid of everything that could cause a cycle. So I can't use these because they connect things that are already connected. And when I use this one, now everybody's connected and all the remaining stuff will be discarded because I've now built what's called a spanning tree. And it's a minimum spanning tree because it's the cheapest possible. It's like building a backbone to the graph to get exactly one path between all the vertices. And what I'm interested in is the total cost of the edges that I have chosen. So there's another algorithm that works a different way. That's his Prim's algorithm. Actually, I think I can't remember which one we just watched. It must have been Kruskal. Let's try this one. Okay, so we start with the cheapest edge. Then instead of picking the cheapest overall, we need to pick the cheapest one connected to that part. So we're kind of like gradually extending. So we pick one of the 3s. Then we need to pick the cheapest option there. So we need to pick one of these 2s. Now we need to pick this 2 because it's the only 2 that we can use to continue. After we pick the 2, well, we're going to be picking a 3 because I have some 3s in here. When there's no more 3s to pick, we're going to start picking the 4s, etc. And whenever something connects things that are already activated, we're going to discard it. We're not going to use it because we don't want any loops. The loops are called cycles. We don't want them. We just want a tree. So now I need to pick one of the 3s. I only have one 3 available here. Now this tree became available, so we're going to use this tree here. Then I need to pick one of these 4s. It doesn't really matter which one. Now I have to pick this 4 because it's cheaper than the 5. And now the 5 became redundant because everything's already connected. So with the same graph as before, but with a different method, we have now calculated a second minimum spanning tree. The cost again will be the sum of the edges that we used, and it's going to be the same exact result as with the other algorithm, Kruskal's algorithm. So let's try this on the whiteboard so we can go very slow. Also remember that there's a YouTube video of this. This is homework 5, question 5. And on YouTube, you can slow it down or speed it up according to your level of boredom and comprehension of what's going on. So let's try this on the whiteboard. This is also something you're going to be doing in the final exam. There's like no way around it. In the final exam, you're going to get a graph. I'm going to be giving you like from 1 to 2, it's going to cost 3. From 1 to 4, it's going to cost 4. 4 to 2, it's going to cost 5. 4 to 3 is going to cost a 6. 2 to 3 is going to cost a 4. 2 to 5 is going to cost a 3. 1 to 5 is going to cost a 2. 3 to 5 is going to cost a 6. 5 to 6 is going to cost a 3. 6 to 3 is going to cost a 2, etc. So you're going to be getting a graph like this in the final exam. And now we're going to make a minimum spanning tree for this. So remember, the trick is to find the cheapest edges first. None of the edges cost 1, but several of the edges cost 2. Let me actually take a picture of this before I start ruining it in case you want to practice on your own. Also easy to practice the exam because you can just generate an infinite number of the questions and grade those on your own. So we need to pick one of the cheapest possible edges. There's a 2 here and a 2 here. So I'm going to activate this 2. So it costs me 2. I pay this 2. So now this edge, I make it thick because it's activated. And the 6 and the 3, they are now also activated. They're included. Now I need to continue. Well, let's use the Kruskal one that just goes with the cheapest edge always, whether or not they're connected. So there's another 2 here. I'm going to pay the second 2. That allows me to activate this edge here. So now the 5 and the 1, they're also active. I've run out of edges of cost 2, so I need to continue with the edges of cost 3. Doesn't matter which one I take first. I'll take this one. I pay 3. Lets me activate this edge, which now included 2. Now, this tree, we're not going to use it anymore because there's already a way to get from 1 to 2. So imagine it's like Ethernet cabling or gas pipes or water pipes. If the water pipe already goes from the kitchen to the living room and from the living room to the bathroom, there's absolutely no reason to make a pipe between the kitchen and the bathroom. It doesn't make any sense. It's either this pipe or this pipe, but not both of them. We don't want to make like cyclic thing easier. We just want to connect everybody. So we discarded that one because it became redundant since these guys are already connected. Now I only have one that costs 3 that's available. So we're going to pay 3 and we're going to connect this. Now I can see that this pipe here, this is also redundant because 3 and 5, they're already connected through 6. So this edge will never be used. Similarly, 2 and 3 are already connected through here, so this edge will never be used. I still have to connect 4. I'm going to use the edge that's cheapest. It costs me 4. So I activate this one here. 4 became connected. And now at this point, this edge is redundant because 2 and 4 are already connected all around the top. And this edge is also redundant because 4 and 3 are already connected all the way through here. So I paid a total of, there's a 5 here and a 5 here. I paid a total of 14 to connect these vertices. Taking another picture. Okay, so that's what we're going to be practicing. Also next week when we do the practice of the graph part of the final exam. But now we need to worry about how to finish this last homework that's related to the same exact concept. So I'm going to take the code for the cross-color one, which is the one I just did by hand. That always picks the cheapest edge. I've already linked it a couple of times today, but let's link it again so that everybody is looking at the same file. If you want to, you can also do it with the prim file. It's not going to be a problem. We're going to the, oh, hey, cool option. See, there's a copy raw contents. Let's click on copy raw contents. So now I don't have to actually go to the raw. They've added this lovely button. So I copied the raw contents and now I have them here. So instead of having to go view the raw, I just copied it. This is very lovely. This is a life quality improvement. Okay, so again, we have a part we don't touch because that's the method. So this stuff down here, you don't need to touch any of this. The thing that our homework is asking us to do is saying that we need to assign a weight of 6 to an edge from 1 to 5. Do I have an edge from 1 to 5? I have 1 to 3, I have 2 to 3, I have 2 to 4, I have 3 to 4, I have 4 to 6, and I have 5 to 6. I do not have an edge that goes from 1 to 5. So I'm going to add one. If you already have it, you're just going to modify it. I'm going to add it here. 1 to 5. And it said I need to make it cost 6. And if yours is already present, don't make a new one, just modify the existing cost to match what you were told that it needed to cost. I messed up my indents. This thing's going to hate me for these spaces, but let's see how much it hates me. I'm going to save it. I'm just going to call it MST. I probably already have an MST. Come on. Okay, so it's going to tell me that these are the edges that it used, and it's going to cost 10. Before I make this change, it also costs 10. And it's kind of easy to understand why my edge didn't change the spanning tree. I added an edge that's much more expensive than any of the existing ones. So there's no way this edge is going to be included if there's another option. And since I can connect 1 to 3, and then 3 to 4, and actually, what's the way to go here? It's the 5 is connected to 6, 6 is already connected to 4, yeah. And since 3 is connected to 4 and y1 is connected to 3, 1 already has a way to get to 5 using only edges that cost less than 6. So my edge is not going to be used. But if the existing edges were very expensive and I added a cheap one, I would probably get a different cost. So with my code in particular, having added my edge did not modify the result. It's still 10. It would have been 10 even before I made any modifications, but that might not be the case for you. It's only going to be 10 if we have added an edge that's really expensive. or we have modified an edge that became so expensive that the other edges are going to substitute it in the structure. Just looking at your graph makes it kind of hard to know for sure what's going to be happening with the cost. So I recommend doing this with the code, but it's not a bad idea to try to draw and reason, is it going to be included or not? Because you need to know how to do this by hand, so you could practice how to do this by hand. And to help the people who want to practice do this by hand, I'm going to go to the whiteboard one more time. If you already understood, just ignore me, vote green when you're done. But I'm going to draw this particular graph with my particular added edge, and we're going to look at the minimum spanning tree. I already turned out the lights. I'm sorry about that. So we had a 1 connected to a 3, and that had a cost of 4. 2 was also connected to 3 with a cost of 2, and 2 was also connected to 4 with a cost of 1. I'm only going to draw the original edges first. 3 is also connected to 4 with a cost of 2. Then I have 4 is connected to 6. That has a cost of 1. And then 5 is connected to 6 with a cost of 2. So what does the original spanning tree look like? This is really easy because the graph is very small. It's obvious that the original spanning tree is not going to use this edge. It's going to use all the others because I have 2 ways of getting to 2. It's either I pay 1 or I pay 2. So I want the cheapest, I'm going to pay 1. So my original spanning tree is going to be using this edge here, this edge here, this one here, this one here, and this one here. And it's going to cost 4 plus 2, which is 6, plus 4, which is 10. And now I'm adding my new edge that's going to connect 1 with 5, but I'm making it cost 6. So there's no way that this 6 would alter any of the decisions here, since it's more expensive than any of these edges here. So it's simply not going to be used. So technically, when your graph is very small and you're very clever and it's a very clear drawing, you can reason what's happening without running the code. But most of the time, this is actually really not going to be the case. Taking a picture for you guys. If you need more time or if you're getting an error, please vote yellow for more time and red for error so we can fix this for you. And let's go take a look at the results to make sure we have our 50 points. Let's go Marvel, if anybody passed the class. So all of this stuff, if you're M4, you should have a 50. And here we have one brave warrior that actually passed the class already. Very nice. Anybody else? Here's another one. Some people are very, very close at 69, 67. Here's a third one who already passed. Fourth one, another 69. Fifth one. So 5 people already passed the class and several others are very close. So now, if you're only a couple of points from passing the class, it's going to be really nice for you in the exam because technically just by guessing, you're probably going to get the correct grade. So you can just worry about learning things for the sake of learning because you're pretty much all set already. You don't really have to stress about it. And you can focus in the exam on the questions that you actually understand. The questions that confuse you, just guess them. It doesn't matter because you have 20 multiple choice questions. It's going to be so easy to pass the class by just knowing a couple of things really well. So next week, we're going to practice all the graph related questions in the exam. Let's look at the exam briefly again. And then the week after, we're going to practice the binary tree questions, plus the last two that have to do with problems and algorithms. Taking a quick look at the final exam. I'm switching the language so it makes it in English for me. Come on, dollars. There we go. So questions 1, order of the graph, size of the graph, density, that stuff we did in homework 3, degree, induced subgraph. We talked about cycles a little bit today. So we're going to talk about cycles, cliques, independent sets, corrected components next week. We've already worked with distance and diameter in the third homework. We're just going to check the weighted versions next week. What we just now did was the minimum spanning tree. So that's question 12. That's where we're going to finish next week. And then in 2 weeks, we're going to build a binary tree like we did today in question number 3. We're going to talk about the leaves, the parents, the children. We're going to revisit the height thing that we talked about last week. We're going to define next week also depth, which is kind of like similar to the height thing, but we go from the root downwards. And then these last two have to do with all the codes we've been looking at, the names of the algorithms, the purposes of the optimization problems, whatnot. So now imagine you're at 69 points and it's the day of the exam and you're just not feeling well. You're going to go in here and you're just going to click A on every single question because your mom's not feeling well, you're not feeling well, you'd rather like to go see a doctor or take a nap and you really don't feel like it, so you're just going to respond A. And now since we have questions, some of them are also, again, like in the midterm, going to have multiple correct answers. So it's going to be really easy to get a couple of points even without reading the questions. The expected value of you responding randomly is exactly at 4, because you're supposed to get 20% correct by random answers. And questions like 6 could have multiple correct ones, 7 could have multiple correct ones, 8 could have multiple correct ones. So there's 3 questions that can have more than one correct answer. So actually it's really easy just by guessing to get like 5 or 6 points as well. If you're lucky, you can get like 8, 9. So next week we practice so that everybody can get 12. And then the week after that, we practice more so that everybody is in condition to get the 20 points. If you have your 50 points now, please read the instructions for the project. You can already, I always forget that the bot doesn't speak English. You can already register your topic if you want to, if you have your 50. What you need to do to register your topic is on this channel here. You need to write what you want the project to be on, tag me, I'll read it and I'll respond to you whether it sounds like a good idea. And then when I've approved your topic, then you're going to send me a direct message with your student number, the group you're signed up in, which is M4 for the most of you, and an expectation of how many points do you think it's going to be worth. The project is 10 maximum. So if you think you're going to get a 7, you're going to send me your student ID, the group, and that you think you're going to get a 7. But this is after I approve your topic. Do not send me anything by direct message until we have talked about your topic on the channel. We do not talk about the topics in private message. Everybody needs to be able to see them because no duplicate topics are allowed. So everybody needs to know which topics you already picked. And if I tell you that a topic isn't good, it's helpful for the others to know not to suggest those kinds of things. And the same, if I approve your topic, it gives the others an example that, oh, hey, ideas like this will work. So we're going to use the channel for that purpose exclusively. And next week, I'm going to start pressuring you guys to register your project topic so that you have a little more than just one day to do those. The project, you need to turn it in by noon the day before the exam. And you don't really mandatorily have to do it. It's only 10 points. So you can easily get a 90 in this course without turning in the project. But if you did poorly in the exam, the midterm exam, it's a really good idea to do the project because that way you get a little bit more of a cushion with points and the exam won't be as stressful because you're a little closer to passing the class before you even present. I'm gonna grade those projects in the afternoon after you guys send them by noon the day before the exam, so that when you start the exam, you already know how many points you got, so that when the exam's graded, you know your final result and you don't have anything pending with me anymore. So I'll catch you guys next week for the first practice of the final exam. Please try to complete all of your homework. It's a huge waste if you don't have the 50 points. If you need help, ask here on the channel. Lots of the other people are also very willing to help. After we do the exam, the following morning, I'm going to calculate the extra points for the MVPs, and I'm going to post those here so that you know on the channel how many extra points you got. And remember, the extra points only appear if the person you helped passed the class. If they fail, no matter how much you help them, you're not getting any commission. The commission is for people who received help from you who actually passed the class. Otherwise, it doesn't count. So if you've been helping somebody and that somebody seems kind of weak, help them more. Make sure that they pass the class so that you can earn your commission. But that would be all from me to you today. I'll be staring at the channel until noon. And at 12 o'clock sharp, I'm going to start over again, the same stuff in Spanish, in case you want to join the V1 group in looking at this stuff again. And I'll see you guys next week. In a few seconds, I'll be posting you the link to the Twitch and I'll be exporting it to YouTube. Take care.